Hello everyone, welcome to my channel. Now in this video we are going to see the Gauss's theorem and a few of its applications. Now Gauss's theorem, it relates the flux with the charge. Now prior to this we have already seen the basic concept of electric flux, and the electric flux, it is related to the electric field by the expression flux is equal to integration of E dot ds. This is how we define electric flux. So that means this flux, it is related to electric field, okay, and we know that electric field is related to charge. So there must be some relation between electric flux and electric charge, okay, and this relation is given by the Gauss's theorem. Gauss's theorem. Now what this theorem says, that if you have a closed surface enclosing charges q1, q2, q3 and so on. Suppose we have three charges inside and this q4 and q5 are outside this closed surface. Then the Gauss's theorem says that the total flux through this surface, it will be 1 by epsilon naught times the charge enclosed, total charge enclosed, okay. Now in this case, this q enclosed, it will be, charge is a scalar quantity, so simply you have to add taking into account the sign, okay. So here all the charges are positive, so q enclosed will be q1 plus q2 plus q3, okay. Now suppose this q3 is with a negative sign, so we have q1, q2 and minus q3 inside the surface, and q4 and q5 are outside. So in that case, the q enclosed will be q1 plus q2 minus q3. So while adding the charges, you need to consider their sign, okay, but these charges will not contribute to the flux through this surface, okay. So that means here the flux through this surface, it will be 1 by epsilon times, for this particular case it will be q1 plus q2 minus q3, okay. So this is our Gauss's theorem, okay. Now let us first verify it. Suppose we have a spherical region, okay, this is a sphere, and at the center of the sphere we have a charge q, okay, and let's say r is the radius of this sphere, okay. Now if we take a small area at this particular point, now for this small area, for this charge in this small area, the electric field intensity is, it is directed in the outward direction, and the area vector, since this is a sphere, so area vector, it will be radially outward direction, normal to this point, so it will also be in this direction. So this is the area vector ds, okay. This is for this small area, okay. So flux through this small area d phi, it will be E ds cos 0 degree. See, flux is E dot s. So here the angle between the electric field and the area vector is 0 degree. So this is E ds cos 0 degree. So we have d phi is equal to E ds, okay. So this is the flux through this small part. So total flux through this entire sphere, it will be, the total flux will be phi is equal to integration over closed surface, for this closed surface E ds, okay. Now E at this point, due to this charge at distance r, it is, so E at this location, it will be E is equal to 1 by 4 pi epsilon naught q by r square, okay. And if you substitute that value over here, so phi will be 1 by 4 pi epsilon naught q by r square integration over the closed surface ds. Now ds is the area of this part, okay. Now if you integrate, you will get the area of the complete sphere, because this is integration over the closed surface. So integration of ds, this will be for this sphere, it will be 4 pi r square, because 4 pi r square is the total area, ds is a small area. Okay, so this is phi is equal to 1 by 4 pi epsilon naught q by r square into 4 pi r square. So this 4 pi r square gets cancelled. So we have phi is equal to q by epsilon naught. So this is the flux through this surface, and it is 1 by epsilon naught times the enclosed charge. Here the enclosed charge is q, so phi is equal to q by epsilon naught, or I can write it as phi is equal to 1 by epsilon naught times q. Okay, so this is the proof of Gauss's theorem. Okay, and now we will see the applications of Gauss's theorem. So the first application of Gauss's theorem is the obtaining the expression for electric field due to a point charge, and that is also the verification of Coulomb's law. Now suppose you have this point charge q at location O, and at distance r at location A. At this particular point we have to find the value of electric field intensity. Okay, now if we are using Gauss theorem, then we need to have a closed surface enclosing the charge. Okay, now in this particular case we have a point charge. Okay, so now you need to draw this surface in such a way that this surface encloses the charge symmetrically. Okay, so obviously if it is a point charge, the surface will be spherical in shape. Okay, so this is the surface. Okay, so this is a sphere, and at the center of the sphere we have charge q, for which we have to find the electric field intensity. Okay, and this surface is called the Gaussian surface. Gaussian surface. Okay, so it is an imaginary surface enclosing the charge, and this surface will be drawn in such a way that it encloses the charge or charge distribution symmetrically. Okay, so point charge, the Gaussian surface will be spherical in shape. And this surface must also be drawn in such a way that the point of observation of electric field must lie on the Gaussian surface. Okay, so this is the point of observation of the electric field. Okay, now this is location A, and so near this point of observation you take one small area. Okay, now obviously for this small area, the area vector will be in the outward direction. So this is the area vector, and for this charge electric field intensity will also be in same direction. So this is E. Okay, so E and ds, they are basically in the same direction. So flux through this small area d phi, it will be E ds cos 0 degree, E and ds being in the same direction. So this, on integration, we have this phi is equal to integration over closed surface E ds. Okay, now phi from Gauss's theorem, it is 1 by epsilon naught times the enclosed charge. So here the enclosed charge is q. Okay, so this is equal to E into ds, integration over closed surface ds. So integrating, so this small area is ds. So if you integrate, you will get the total area, that is total area of the sphere will be 4 pi r square. Small r is the radius, so it will be 4 pi r square. So if you bring this term over here, we have E is equal to 1 by 4 pi epsilon naught q by r square. So this is the expression for electric field intensity due to a point charge q, this charge at a distance r from it. Okay, now so this is the expression for electric field due to a point charge. Then verification of Coulomb's law, that is, if we place a charge at this particular point, if I place a charge q naught, okay, then the force on the test charge, this charge will be F is equal to q naught into E. So that's F is equal to 1 by 4 pi epsilon naught q naught by r square. So this is the force on this charge q naught due to charge q, and this is your Coulomb's law. So this is how we can verify Coulomb's law using Gauss's theorem. So this is the first application of Gauss's theorem. So next we will calculate the electric field intensity due to a uniformly charged infinitely large sheet. Okay, now there are two kind of sheets, like thin sheet and a thick sheet. Okay, now if we have a thin sheet, okay, what do you mean by thin sheet? Like suppose this, my hand is a sheet, okay, and suppose this chalk is a charge, and if I place this charge over here, okay, so now the charge is on the sheet. Now if I am observing this charge from this side, so I am observing this charge, okay, so if it is a positive charge, electric field intensity at this particular point will be directed in this direction, away from the positive charge, okay. Now if I am observing this charge, same charge from this side, again the electric field due to this charge at this particular point it will be in this direction, but for both location the same charge is producing the electric field, okay. So suppose we have a large thin sheet and it is having some positive charge, it is uniformly charged, so say sigma is the surface charge density, okay. So now if I take, if suppose this is the point of observation of electric field, okay, so I am drawing one Gaussian surface over here, so this is the Gaussian surface, okay. Now identically this side also there will be a point of observation of electric field, similar point I am taking here also, so I am extending the Gaussian surface to the other side also. So this is the Gaussian surface. So for this side, this is the direction of electric field intensity and this is the area vector for this small area, okay. Similarly for the other side, this is electric field intensity and this is the area vector, okay. So the total flux will be d phi, it will be E ds plus E ds in this direction, E ds in this direction. Though they are in opposite direction, flux is a scalar quantity, so we have to only add them directly. So this is d phi is equal to 2E ds. So if I integrate, I will get the total flux integration over the closed surface. So for the entire surface, it will be phi is equal to 2E s, okay. Now this is equal to, if I apply Gauss's theorem, 1 by epsilon times the enclosed charge. Now sigma is the surface charge density and s is the area, so total charge will be sigma into s. So this s and this s cancels out, so we have E is equal to sigma by twice epsilon naught. So this is the expression for electric field intensity due to a uniformly charged thin sheet. So as you can see, this electric field intensity, it is independent of distance from the sheet. It is E equal to sigma by 2 epsilon naught, so it is a constant. So it shows that near the sheet the electric field intensity will be uniform, and if the charges are positive, so electric field intensity will be normal to the plane of the sheet, it will be directed away. On this side it will be in this direction, on the other side it will be in the opposite direction, okay. So this is the expression for electric field for thin sheet, okay. Now what happens if it is thick sheet? Now if it is a thick sheet, then suppose the sheet is positively charged, so this side you have this charge, okay, this charge, and suppose this is a positive charge and this is another chalk, so another charge, okay. So now though both sides you have positive charges, but electric field which is produced on this side in this direction, it is produced due to this charge, okay, and electric field on the other side, it is produced due to this charge, okay. So these two charges are different charges, though they have same sign, same nature, but the charges are different. We have two charges producing two different electric fields, though they have same expression, but the charges are different, okay. So because of that, what happens now? Suppose this is a thick sheet, okay. Thick sheet means a plate, okay, infinitely large plate which is uniformly charged. So this side positive charges, the other side also you have positive charges, but we are not able to see on the other side. So that side also, this side also will have positive charges, and here also sigma is the surface charge density, okay. So again we will be drawing the same similar Gaussian surface as in the previous case. So this is the Gaussian surface, so in this direction we have E and again ds, here also we will have E and ds. So similar to the previous one, we have phi is equal to 2Es, that is equal to 1 by epsilon times the enclosed charge. Now here the enclosed charge will be sigma into twice s. Why twice s? Because now we have two different surfaces. Okay, charges are on two different surfaces. So here we have twice s. So this 2 and 2 cancels out. This ss cancels out. So we have E is equal to sigma by epsilon naught. So this is half of the previous value, but again we can see that electric field intensity, it is a constant quantity. So near a thick sheet, uniformly charged thick sheet, again the electric field intensity will be normal, and if the sheet has positive charges, it will be normal in the outward direction. If negative charges, it will be normal inward direction. So next we will see electric field due to infinitely long line charge, uniformly charged infinitely long line charge. Okay, so suppose this is a line charge, okay, and it is having positive charges, okay, and it is infinitely long, so it is going in this direction also infinity, this direction also infinity. And suppose this is the point of observation of electric field and it is at a distance r. Okay, now as I told you, if you have to apply Gauss's theorem to find the electric field intensity, you must draw a Gaussian surface, and this Gaussian surface must enclose the charge distribution symmetrically, and second condition is the point of observation of electric field must lie on the Gaussian surface. So if it is a line charge, obviously the Gaussian surface will be cylindrical in shape. So we are drawing a cylinder such that the radius of the cylinder is r and length of the cylinder is L. Okay. Now this is the point of observation of electric field. So surrounding this point, you take one small area. So for that small area vector is in the outward direction. For the charges, this is positive charge. So electric field intensity in this small area will be in the outward direction. So it is E. So both E and ds, again they are in the same direction. So angle between E and ds is 0. So while calculating the flux, we need the angle between E and ds, electric field and area vector. So the flux through this small part d phi, it will be E ds cos 0 degree. So that is d phi is equal to E ds. Okay. So if we integrate this, integration over closed surface, so we will get the total flux. So this is total flux E is equal to, so the total flux phi is equal to E into ds, integration of ds. So ds is the small area. So if you integrate, you will get the total area. So that is twice pi RL. Okay. Now you may have one doubt that I have taken this curved area, but what about this area, top area and this bottom area? See, for this the area vector will be in this direction, okay, and electric field intensity is in this direction. So this angle is 90 degree. So angle between the area vector and electric field intensity is 90 degree. So flux through this surface will be 0. Similarly for this surface, area vector will be in the downward direction, electric field is in this direction. So again for this also the flux is 0. So flux will be only through the curved portion. So that is why only I am taken only the curved portion. So this area is for the curved portion, that is E into twice pi RL. Okay. Now what is flux? Flux from Gauss's theorem, it is 1 by epsilon naught times the enclosed charge. So enclosed charge in this length L, if lambda is the linear charge density, okay, linear charge density means charge per unit length. Okay, so in unit length you have charge lambda. So in L length, the enclosed charge in this Gaussian cylinder, length is L, so the enclosed charge will be lambda into L, because lambda is the charge on unit length. So in L length you have charge lambda into L. So if I equate these two quantities, I have lambda into L by epsilon naught is equal to E into twice pi RL. Okay, so this LL cancels out. So we have E is equal to lambda by twice pi epsilon naught R. So this is the expression for electric field due to a infinitely long uniformly charged wire or a line charge, infinitely long line charge. And as you can see here, E is inversely proportional to R. So as you are very close to the line charge, the electric field intensity will be very high, and as you move away, the electric field intensity will keep on decreasing, and at infinity, the electric field intensity will become 0. Okay, so this is for a line charge. So next we will calculate the electric field due to a uniformly charged conducting sphere or a hollow sphere or spherical shell. Okay. With regard to behavior of electric field, a conducting sphere, solid conducting sphere and a hollow sphere are same, because in both cases the charges cannot reside in the interior part, charges are on the surface. Okay. So whether you have a conducting sphere, okay, or a hollow sphere, the charges are on the surface. In a conductor, charges cannot reside in the interior of the conductor at any location inside. So charges will be on the surface. So suppose Q is the charge and R is the radius. Okay. So now suppose this is the point of observation of electric field, and this is at distance R, which is greater than capital R. Okay. So for this charge distribution at this point, if you want to calculate the electric field, and since there is no surface at this particular point, we need to draw imaginary surface, that is called the Gaussian surface. So for this sphere, what kind of shape will you draw so that that Gaussian surface is enclosing this sphere symmetrically? Obviously, you will be drawing another sphere. So suppose this is a sphere, so you will be drawing another sphere, okay, and whose radius is small r, which is greater than capital R. Okay. So for this point, again we take one small area. So this is ds. Electric field intensity is also in the radially outward direction, so it will be in the direction of ds because positive charges. Okay. So applying Gauss's theorem, we have phi is equal to E ds equal to integration over closed surface E dot ds. So again I am not writing the cos 0 term. So this is E ds. It is equal to 1 by epsilon naught times the enclosed charge. So charge is q. So this is q. Okay. So this integration over closed surface ds will be the area of this Gaussian sphere, and since the radius is small r, so its surface area will be 4 pi r square. So this is E into 4 pi r square is equal to q by epsilon naught. So E will be 1 by 4 pi epsilon naught q by r square. Okay. So this is the expression for electric field intensity outside the sphere. So here we can see that E is inversely proportional to r square. Okay. Now similarly, if the point of observation is on the surface, okay, so if you are on the surface, you need not draw a Gaussian sphere or a Gaussian surface, because already you have a surface available. So if you treat the same, if you give the same treatment, instead of small r, you will get capital R. So on the surface, you will have E is equal to 1 by 4 pi epsilon naught q by capital R square. Okay. So this is the value of electric field intensity on the surface. Okay. Now how about the inside? Now for inside, suppose this is the point inside and this is at distance small r, which is less than capital R. So that means you are inside. So now if I draw a Gaussian surface, now inside this Gaussian surface there is no charge. Okay. So for this, phi is equal to integration E ds is equal to 1 by epsilon times the enclosed charge. In this case it is 0. Okay. Since enclosed charge is 0, this quantity E should also be 0. Okay. If I equate these two, you get E is equal to 0. So it means in the interior region, the electric field intensity will be 0. Okay. So let us summarize this result. So in the outer region, we have R greater than R, and E out, electric field outside the sphere, it is 1 by 4 pi epsilon naught q by r square. So that is E out is inversely proportional to r square. Now on the surface, that is R equal to R. Here this R is greater than R. On the surface, R is equal to capital R. So we have E surface, E surface equal to 1 by 4 pi epsilon naught Q by capital R square. Okay. Now this R is greater than this R, so obviously this electric field will be less than this electric field. So surface you have maximum electric field, and outside the surface as you move, the value of electric field gradually decreases. Okay. Now in the inside region that is R less than capital R, E in is equal to 0. Okay. So this is in the interior region, electric field intensity will be 0. Okay. So we can show this graphically. So this is electric field, this is R equal to R on the surface. If you are inside, so this is R less than R. If you are outside, so this is R greater than R. Okay. So from center to the surface, just before the surface, inside the surface, electric field intensity is 0. On the surface, electric field intensity is maximum. So this is E surface is equal to E max, and outside the electric field intensity gradually decreases. So here E out, it is inversely proportional to R square. Okay. So this is the behavior of electric field intensity if you have a uniformly charged conducting sphere or a hollow sphere. So next we will calculate the electric field intensity due to uniformly charged non-conducting sphere, that is charge is uniformly distributed throughout the volume. Okay. So this is the sphere of radius capital R, and the charges are distributed throughout the volume. It is uniformly charged, say Q is the total charge. Okay. And so for this particular case, see in the outer region again the enclosed charge will be Q. If you are on the surface, again the enclosed charge will be Q. So in the outer region and on the surface, the behavior of electric field intensity will be same as in the previous case, that is for a conducting sphere or a hollow sphere. Okay. So in this we will only calculate the electric field intensity in the interior region, in the interior of the solid non-conducting sphere. Okay. Now suppose this is the location and this is at R less than capital R. Okay. So this is R less than capital R. At this location we are going to calculate the electric field intensity. Okay. So now again we will draw a Gaussian surface. So now we are bothered about the charges which are inside this sphere, this Gaussian sphere. Okay. So here inside we are going to calculate the electric field inside. So R less than R. So phi is equal to E in ds is equal to 1 by epsilon times the enclosed charge. Okay. Now total charge is Q. This Q charge is distributed throughout the volume. So Q by 4 by 3 pi R cube. This is the charge per unit volume. So if I multiply this with the volume of this sphere, that is 4 by 3 pi R cube, I will get the charges which are on this part. Okay. So this 4 by 3 pi cancels out, and this integration over closed surface ds, it will be 4 pi capital R square. So simplifying this, you get E in is equal to 1 by 4 pi epsilon naught QR by R cube. Okay. So this is the expression for electric field intensity in the interior region. So here see Q, capital R, all these quantities are constant. So E in, it is directly proportional to R. Okay. At the center, this small r is equal to 0. So electric field intensity at the center will be 0. And as you move in the radially outward direction, electric field intensity is directly proportional to R. So as R increases, the electric field intensity also increases linearly, and it will acquire a maximum value on the surface. And outside the region, we know that E out is inversely proportional to R square. So in the outer region, the electric field intensity will gradually decrease. So let us see this behavior graphically. So this is electric field intensity. This is on the surface. So this is R equal to R. So if you are inside, this is R less than R. If you are outside, so this is R greater than R. So in the interior region, this is directly proportional. Center it is 0, so it is a straight line. So this is E in, it is directly proportional to R. So it increases linearly, electric field intensity increases linearly, acquires a maximum value at R equal to R. So this is the maximum value and that is the maximum value at surface. So this is Es is equal to E max, and in the outer region electric field intensity is inversely proportional to R square. So this is in the outer region, that is R greater than R. E out is inversely proportional to R square. Okay, so this is the behavior of electric field intensity for a uniformly charged non-conducting sphere. Okay, now these are the basic concepts related to how to calculate the electric field intensity. Now for this there is one more additional topic, that is electric field intensity inside a cavity. So if you wish to watch that video, please do comment in the comment box. I will make a video for that. Otherwise, based on this concept, if you are able to derive that expression, then it is well and good. So my best wishes to you. Good luck.